if I want to buy a meal, I cannot have it good, fast, and cheap.
Yeah.
I need to choose two. I cannot have all three. There's like these three things that we'd like to have in nature. We can't have them all. The math is showing that we don't have them all.
This video is about a brilliant physicist whose work almost went unnoticed. If it had, we wouldn't know about quantum entanglement, quantum teleportation, and quantum computers would be science fiction. I'm talking about John Stuart Bell, whose Bell's inequality test led to the discovery of perhaps the strangest quantum phenomenon, non-locality.
The particles, in some sense, communicate faster than light.
And now we know it cannot be a prearranged thing. And we don't have general relativity giving us the option to communicate faster than light. So that's also ruled out.
Yeah.
So we have non-locality.
So this is a new phenomenon.
Yeah.
Let me give the full details of it.
I sat down with physicist Lídia Del Rio and Professor Sandu Popescu to try and really understand the work of John Stuart Bell. We discussed non-locality, entanglement, and the role of time in quantum mechanics. Does quantum not have the arrow of time?
These results don't show that information is traveling back in time. They just say it's much easier to predict what happened at an intermediate time if you think of it having come back in time.
Yeah.
Right? It's just a simpler theory.
Are measurements influenced from the future?
The math that you do just thinking in the ordinary way going forward is extremely complicated. While the math, putting like this, is immediate and very intuitive. So the math itself tries to tell you there is something interesting there.
Welcome to the Essentia Foundation's YouTube channel. We are sitting here in Vienna covering a conference about the foundations of quantum mechanics. It's hosted by the ICOKI Institute, celebrating 20 years ICOKI and 60 years of Bell's theorem. And our guest today is an eminent physicist, Sandu Popescu, professor of physics at the University of Bristol. And you have a long-standing career in physics, in quantum foundations, and have been honored by a Dirac Medal. You are you have won the John Stuart Bell Prize, and you are a fellow at the Royal Institute.
So it's Royal Society.
Royal Society, excuse me. Yeah. And next to you is sitting a postdoc of you, Lídia Del Rio, research fellow at the University of Zurich, research fellow of the Essentia Foundation, I should say, who holds a degree, a PhD in quantum information. And it's great to sit down with you here. I'll be asking questions to you, Sandu.
Yes.
And Lidia, it's so nice for you also now to join in with content of ours, as you are a research fellow of our foundation. And in our conversations leading up to sitting here, we discussed that you can join in where stuff gets a bit more technical to help translate to our audiences. I'm not a physicist, and quantum is weird to me. It's very, very weird to me.
Quantum is weird to everyone. That's exactly what we are trying to do, to bring it down to earth.
What I find sort of confronting, if we just look at the history of science, that with quantum theory, we always thought there's an observer-independent world that can be discovered through science. Laws can be extrapolated and extracted from it, and then we can predict nature's behavior, and we can confirm our theories about nature, and then we talk about universal laws of physics, etc. And then quantum theory comes along, and it does give us a very accurate description of nature, but it won't show us its deepest mysteries in a sense. And I'm talking, of course, about the superposition itself cannot be observed. We can only, perform a measurement.
No. You observe direct consequences of things being in a superposition.
But exactly, that's the word, right? We observe a consequence of, and not the superposition itself? Or?
For everything we observe consequences of. You don't observe a force acting on this cup, but if I act on it, it gets accelerated. You haven't seen the force doing there. So everything we see consequences. And then it is an interesting interplay. We try to form theories about what is going on. And the theory would be very nicely described by a conceptual object that is called force. You haven't seen a force here. You may imagine like a little arrow pointing in that direction and so on, but this, you haven't seen that. What you see consequences, and then you adapt some concepts that allow you to manipulate these consequences in a very systematic way.
You mentioned that nice quote and image from Feynman, right? And there's of course the more cliche Feynman quote that isn't it that when you think you understand quantum mechanics, or if you say you understand quantum mechanics, you don't understand quantum mechanics, right?
I think that what he said, he presented a specific experiment that encapsulates a lot of things that are counterintuitive. And he said that this is, well, in his view, the only mystery. And he said that basically nobody understands it.
And if we...
What was this experiment?
Well, the two-slit experiment with electrons.
He thinks nobody understands the two-slit experiment.
Well, deeply of how that thing happens. It is trivial to compute the consequences.
I'd like to hear your double slit.
So in that sense, let me state something that many times may be confused. Just the simple fact that you can be given a specific situation and you can compute the consequences, it doesn't really necessarily mean that you understand it deeply what is going on there.
Yeah.
Okay? To understand it deeply what is going on there, you should have an intuitive way of thinking what happens if I modify that experiment. And more than that, what is something interesting to do, not just to compute. So in this particular case, which is pretty simple, the one that you mentioned of Feynman, you just have a source here from which you can shoot electrons. It may be a tiny wire through which you put a current, and it becomes very hot, like a filament in the old bulbs, and an electrode in front of it to accelerate. And sometimes an electron will evaporate and will be shot out of it. And you put in front of it a screen with two tiny holes, and behind it another screen. And you look what happens in that situation. Interesting things happen. Obviously this is a thought experiment. In reality, nobody did it that way. But the question is what is happening in the back of that screen is very interesting and very counterintuitive. And that's why he claimed that this is a true mystery. Because every single time an electron arrives, like a bullet, one entity, boom, boom, never half an electron, it's not broken, not anything. But it feels that both holes are open. If you close one of them, it's not that sometimes it doesn't go through and sometimes it goes through the other, but something different happens. In some way, as if the electron feels both little holes open. That was his mystery. And it remains, up to the present, one of the things that most people are fighting over it to say what its significance is. Which shows that we still don't understand it very deeply.
Yeah.
I believe that there is at least one way of understanding, but let's leave that for later.
I'm very curious though what your explanation is. Can I recap and please correct me where I say stuff wrong for our audience, just to get back to the double slit experiment. When we fire an electron and two slits are open, we see an interference pattern, right? So it is
something that is called an interference pattern.
Yeah.
So exactly like if you would be on the beach behind the dam and you see waves coming from the two sides of the dam, and then when both of them are on a crest, you see it even bigger. When one is a crest and one is lower, you see the water almost not moving. Yeah. And you see a very interesting fringe thing, which is based on the fact that this wave comes from the two sides. Yeah. Now, behind the behind the two holes through which the electron could pass and up to the screen, you see, if it falls on a photographic plate, you see just one dot. Every time an electron comes, there is just one dot. But if you send many of them, these dots, one after the other, at no time there are more than one electron in flight, these dots arrange themselves in a pattern of fringes, although you've never seen any wave going through both slits together. And that is the mystery of what is happening there.
It's really puzzling, yeah, to me, because I could sort of grasp, okay, wave-like behavior, interference, but that's with many electrons, but then single electrons, because the screen would go here and the electron here, bum, bum, bum,
exactly.
bum, bum, and then we have this pattern, and then the thing is, right, but correct me if I'm wrong, there is no way to predict where a single electron will hit the screen, right?
That's correct.
But we can very accurately predict
how they will arrange,
and that is super accurate, right? Isn't it one of our most accurate theories of nature?
Yes, I mean, yeah.
Yes, that's correct. Yeah. That's correct.
So we have nature at its most fundamental level, at the particle level, being totally probabilistic or random.
Yes.
And then we have a perfect probability distribution.
No, I think that...
But this is the same as if I have a biased coin that I say, one side is a bit heavier or tilted or so. I cannot predict the outcome of a single toss, but I can say that if I make 1,000 tosses, maybe around 700, plus minus a little bit, will be heads, and about 300 will be tails, right? So it's the same idea, right? I can make a prediction about the probabilities of where the electron will hit, right? But of course, it's still very vague. But then if I send 1 million electrons through it, then the pattern should be fairly clear. It's a law of large numbers.
There's one question I have, though, there, because the toin, I get that, but that's a different notion of probability, right? Because it's the idea then, in theory, under Newton and Einstein, I could have all variables with that coin. And then I could, if I had this, and that's Laplace's theorem, I could perfectly predict it.
Yes.
But we know that cannot be done in quantum theory with a single particle.
Yes, that's precisely the point.
Yeah.
So quantum theory is, at a fundamental level, non-deterministic theory.
Yeah.
Even if we know all the details we repeat the experiment in exactly the same condition, we don't know what will come out.
Yeah.
Incidentally, this was seen as a drawback of quantum mechanics. Einstein, he was one of the fathers of quantum mechanics by the discovery of photoelectric effect. But as it happens many times with parents that get displeased for what happened, into what their children got transformed, Einstein became very displeased of quantum mechanics because he couldn't believe that quantum mechanics is non-deterministic. And that's why his also famous phrase, God doesn't play dice. However, one should appreciate that a theory that is non-deterministic or probabilistic at a fundamental level is a much richer theory. It allows many things to happen what could not happen in a fully deterministic theory. A deterministic theory is, if you wish, a subclass of the non-deterministic one. So you gain a lot of liberty in theories that are non-deterministic. They are far more interesting and...
That sounds interesting, but it also sounds a bit philosophical to me. I like it sort of more from a philosophical level that I like.
Well, it depends how you...
creativity in our universe, for instance. It brings with me, okay, then I have a universe that is at some level truly creative and not determined. And I like that as a sort of, but that's almost psychological. I like that psychologically.
Well, in some sense, you may think it's philosophical, but of course it depends how you define philosophy. But also in a pragmatic way, there are effects that would contradict many other principles that you believe are there in nature. which are impossible in theories that are fully deterministic, and suddenly they become possible in a theory. Well, non-locality and things like this, like in Bell inequalities, and many others.
Yeah, there's so much I'd like to touch on with both of you, but it's nice to pick up the thread where we left it with the double slit experiment, because we then have Einstein deeply troubled by this deeply probabilistic random nature.
Indeed.
So he's troubled by that, and you have the Bohr-Einstein debates about all of this. And then Einstein coming up with Podolsky and Rosen with the famous EPR paper. That was the 30s, I think, or 20s. 35, yeah. 35. Basically saying, correct me if I'm wrong, if quantum theory is a complete or correct description of nature, one of its implications is what was later called, it wasn't in the paper, but spooky action at a distance, right? Is that...
No.
Oh, sorry.
No. You are partially correct.
Thanks.
So, Einstein was troubled by the fact that quantum mechanics was considered to be probabilistic. So he tried to find a way to show that that actually it is fully deterministic. As a matter of fact, Einstein for many years, he tried to prove that quantum mechanics is factually wrong. And he tried to find all kind of thought experiments that will show that a prediction of quantum mechanics cannot well, it's contradicted by the experiments. He wasn't able to do that. One famous event was at a conference, one of the Solvay conferences in Brussels, where Einstein came with an example that, according to him, was showing quantum mechanics is wrong. Not that has philosophical difficulties and so on, but factually wrong. And all the great physicists were there, and they were all shocked. And that's how they went, to bed. But next day, Bohr realized that Einstein forgot a consequence of Einstein's own generalized relativity thing. And once you take that into account, quantum mechanics turns out to give the right answer. Mm-hmm. So from that moment on, well, I'm not a historian of science, so maybe I get my dates not exactly in order, but the point is that at a certain moment Einstein stopped trying to say that quantum mechanics is wrong, but that is simply incomplete. That when we think that we described all the parameters in the game, and it's still we cannot predict where particles will end, then it is more that we didn't take everything into account. And then it will become really like flipping a coin, where if we know exactly how my hand moves, exactly how the air was at that moment, we can immediately say exactly which face of the coin will come.
Yeah.
And one of those situations was all these things as they are originally discovered, they are put in a more complicated way than one could do. The simplified version is that you have a source that emits two particles, and they go to measuring devices, far apart. And what exactly the measurement is irrelevant. Let's say the only important thing, the measurement has two different possible outcomes. Either a red light bulb will light up or a green one. And each particle comes, a light bulb on its own measuring device will light up. Now, it turns out that later when you look at correlations, you find out that it is either the case that both red one or both green one. Never a red on one side and a green on the other side. So Einstein asked, how is this possible? Well, one way would be if the particles sort of talk to each other and they say, look, I decided to say red, you see what you're doing. and the other one will do that. And to avoid this, Einstein imagined, let's separate those measuring devices very, very far. So that, because I know, Einstein said that nothing propagates faster than the speed of light. This was his own relativity concept. He said, it doesn't matter, they may carry mobile phones, they may carry whatever, they cannot talk to each other. So if they will have to make a decision on the spot, if it is not in advance decided what they will give, whether they will light up a red bulb or a green one, then they cannot coordinate. So it must have been that actually when they were at the source, they already decided, we will say red. So they go there and they say red. When you repeat it, they may say, we will say green. They go and they say green. But this means that actually somewhere in the mind of this electron, that there must be some variables they need to remind themselves of the decision. So there is another parameter there. And everything is perfectly well defined in advance. So their paper essentially introduced what is called local hidden variables. A decision made in advance which goes beyond quantum mechanics. Quantum mechanics said there are no other variables in the mind of the electrons. So they were actually very happy with this. It was much later when John Bell just changed a little bit the setup. That was in 1964, and this conference celebrates...
It's quite a bit later, actually, right? That's like 30 years in between. Was the physics community in those 30 years all okay with the EPR paper?
Well,
was the physics community, yes, okay, we have local hidden variables?
Well, this shows that, something that should be obvious. While physics is, is universal and it's, it's what nature is, physics is made by physicists, who are human beings that have all the qualities and the drawbacks of any other human being. So there are all kinds of sociological aspects of how to make science, okay? Not of the scientific facts. Facts are facts. But of the way in which people do. This was at the very beginning, very close to the beginning of quantum mechanics, and physicists had a lot of things to do. Quantum mechanics was a very good tool to finally explain things that they were interested in. What are atoms? Why do certain atoms connect to each other to form molecules? What is this thing called chemistry? What are nuclei of the atoms made of? A lot of things. So they had this tool that worked. So then they went ahead to use it. And if it was a good tool, you use it. And, like doctors in olden times, they were prescribing you aspirin and you were happy that it worked. You didn't try to analyze what the aspirin does to your body and so on. Yeah. So although there was a little bit of debate, and although Einstein was such a big figure, nobody cared. They went back home. They went back home and they started to do their own things.
Yeah. I mean, there were also other things going on in Europe and the US in the 30s and 40s that occupied physicists. And also, it's like Sandu said in the Feynman analogy, we did not know what we were looking for, right? That's why it takes so long. It's not like we could see the bubbles in real life. But there were experiments we want to see, right? All this, like you said, like the things that we know, like atoms, molecules, things. We didn't know what to look for in this entanglement of these things.
And more than that, I gave you a simplified view of the paper of Einstein, Podolsky, and Rosen. The way in which the paper was written was far more complicated. The answer that Bohr gave was even more complicated. So it is not that people were presented with something very clear, some conundrum or whatever, and they could see. It was very, very obscure. Now that we go and read it, we now know what is a simplified form.
And before we go dive a bit deeper, of course,
Yes.
making the move to Bell 30 years later, sort of a meta reflection I have is that you see what I like about those early days of quantum mechanics is very much the philosophy as an outstander. I'm not a physicist, so I like
Yes.
reading about the Bohr-Einstein debate, Schrödinger, and I just like all of that. And it seems to me the brilliance of Einstein was that he made that sort of, in a sense, philosophical reflection, because he had sort of difficulty with the metaphysical implications if this theory was complete. So that made him write this. And then you're referring to the fact, of course, that the sort of shut up and calculate mentality that sort of governs, so to speak. I mean, you can say more, but students, there was just a lot of, the bombs were to be built, as you're suggesting, you're like Lidia, in the Second World War.
There were indeed many things going on, and not so many physicists around. And, and there are also fashions in the thing.
And is it sort of, before we go for, do you, both of you think that more deeply, a bit more philosophical, metaphysical reflections is a bit more back in the physics community now? I'd say so, looking at a conference like this, the stuff being reflected on.
I mean, if you come to the conference on foundations of quantum mechanics, you'll find people thinking about foundations of quantum mechanics.
Okay, but are those foundations?
But you haven't seen...
But do you I'm referring sort of to the more sort of philosophy, the metaphysics of it. Okay.
Well, you haven't seen... Well, this is not a conference on philosophy of physics. Go to one of them and it will be incomprehensible because of all kind of tiny details in various interpretations. I think that probably the honest view is that it is a very counterintuitive. Nature at that scale is very counterintuitive. And people are trying to make sense. And it is not easy. Because of that, there are all kinds of debates trying to find their way. Some of them are useful and constructive, others are not, as always. But it is also the case that there were years where trying to focus on fundamental of quantum mechanics was thought as being a non-starter. And people were told that if they would focus on this, that is the end of their career. That's what I was told,
There's
for
actually
example.
this book, do both of you know David Kaiser? He's a great historian of physics, and he's a physicist himself. He wrote this book called How the Hippies Saved Physics.
Yes, I know.
And he is, of course, a provocative title, but what he means to say is that in a certain community of physicists who were a bit more open to weird, crazy ideas, and then that he calls hippies, but they gave a lot of attention to the paper written by John Stuart Bell.
Yes,
and
indeed.
because that's also, I found very interesting that paper was for a time dormant. It
was dormant for 30 years.
The paper of the EPR paper, or you mean the Bell paper so
of Bell.
long?
Yes. So there were a few experiments. Well, two of the people that made the early experiments got the Nobel Prize. But if you would think how many people were interested in this, the numbers probably you could count on, the fingers of your
That's bizarre. Because both of you, just to explain to people who do not know it, what's the importance of the Bell paper, the Bell's theoremist work, Lidia? If you have to explain it to a lay audience, what was sort of his brilliance of his?
It's really like ruling out these ideas of no, quantum mechanics is just an emergent theory. There's something deeper below that is intuitive as we know it, right? That there's like these local hidden variables, like the true variables. And he rules this out. In a way, he makes a no-go theorem. But this is the philosophical implication, and then there was many other no-go theorems.
There is
In practical terms, this kind of theorems, this kind of no-go theorems actually also give rise to like a bunch of results in cryptography, in like trying to make secret key arrangements.
That came later.
This came later. Yeah. But you see, it's not just, and this is something that we recognize now, and it's one of the reasons why the foundations community is like the largest that it has ever been. Not that most physicists think about these things, but there is a community doing foundations. It's largely you can get funding for it. And one of the reasons is that by thinking about these fundamental problems, we can also get practical applications like for cryptography or generating true random numbers or these kind of things, right? And this is, in the end, one of the practical applications of Bell's theorem. But philosophically, maybe...
No, the issue is why it was dormant for 30 years. And that is... You are absolutely right why I made it non-dormant now and why there are billions put into studying this. Because the entire idea of quantum computing and quantum information, all of them have at their core this phenomenon discovered by John Bell. Basically, it tells that if you and I would like to play the role of the two particles that are emitted out, like in the experiment of EPR, but just giving some different types of results there, if we would try to do that, we would need to communicate with each other faster than the speed of light. Okay? And that would seem almost an impossibility given what Einstein was saying, that no signal can communicate. And indeed, nobody could use our communication to communicate. And everything is covered by the fact that we give apparently random results. And they could only see that we are communicating faster than light when they come and compare our results, which is already a posteriori, takes time. But the fact that things are communicating, if you and I were to try this, we couldn't do it unless we communicate faster than light. That was the meaning of Bell. But some people thought this is wrong. And
so he ruled out the fact that you and I
from
the onset had a prearrangement. Bell said you cannot make that prearrangement. Is that
because it's not like the measurement is, we know that, so say Sandu and I, we go far away. It's not like we know that you'll ask us a certain number of questions and we arrange in advance what we'll answer. It's not this.
Tea or coffee.
It's like we go far away and then you ask me a random question that I never heard before.
No. Because you could have known. So, for example, tea or coffee, or chocolate ice cream, or lemon ice cream. And I don't know which of the two questions you will ask.
Yeah.
Okay.
Yeah.
So we need to be prepared what to say to tea or coffee, or what to say to to the two other variants. And then we look at what did you say, how many times it happened that you choose coffee and you choose lemon ice cream.
Yeah, exactly. And then you see how often they are opposite.
How often things are opposite and so on.
Yeah, that's the spin up, spin down, right? And we see that when you measure spin down, you have spin.
In various directions.
It's not like I always reply tea or always reply coffee. If you just look at my statistics, like half the time at random I replied tea and half the time I replied coffee. But whenever I said tea, Sandu said we need to choose coffee. Sandu also said tea. And whenever I said coffee, Sandu also said coffee. Whenever I said chocolate ice cream, Sandu also said chocolate ice cream. Whenever I said lemon.
Yeah. And like 1,000 times, millions times,
always. 1,000 times, yes.
You do many times, and there are specific correlations that can never occur.
And can we do this with particles? Can we perform multiple measures on those particles?
Those entangled particles? You send a pair of particles, and you measure it. Then you send another pair of particles, and you measure it.
So you cannot do, because now we're saying Sandu and Lidia are different, somewhere galaxy away, and tea coffee question, and we see that it keeps on correlating. We cannot do it multiple times with one entangled pair of particles that are sent apart.
No, not with one entangled.
You have 1,000 Sandus and 1,000 Lidias.
Okay, we can make sure that the.
But look, let me give the full details of it. Okay?
Yeah, please.
Suppose that we come to a measuring. We may discuss at the source, and then we are taking to two different rooms.
Yeah.
Okay. And all we have to say, we have to choose a color, like before, green or red. Okay. The only thing is that in that room there is a referee in the room where you go, and the referee shows you, it's either question 1 or question 2. Okay? If it so happened, and the same with me, if it so happened that my referee told me it's question 1, and your referee said it's question 1, we have to choose the same color. If for me it was question 1, for you question 2, again the same color. If it was question 1 for you and question 2 for me, again the same color. But if for both of us the referee showed question 2, we must say opposite ones. Mm-hmm. Now, this is very difficult to arrange for us to win every time. Because suppose we say, so again,
because you don't know that when
for any combination apart from question 2 in both sides, we must say the same.
Yeah.
So we decide I will say red here for question 1. You should also say red for question 1. Yeah. But I don't know what you will be asked. You don't know what I ask. Yeah.
So there's no algorithm for this.
For 1 and 2, we need to give the same answers. But you already know that for 1 I would say red, so you will say red also for 2.
So this is the brilliance of Bell, that he came up with a way to test EPR.
Exactly.
But you just said, Lidia, what fascinates me is that, and that's what you guys, you physicists, call no-go theorems, that you can mathematically, before the experiments were done, already prove it. What's the way to say it? Please explain this.
Okay, I'll explain. So he can formulate this problem exactly like Sandu said. Okay, there's nothing about quantum theory here. He just says, we have these two people, we do, there's like these questions, and they win the game if you know the answers.
How many times they
win, right? And then you can write down, well, if there's a strategy that they arrange in advance, they can only win 3/4 of the time.
Yeah.
Like, for example, they decide to always say green, right? So they always win unless you ask question 2 in this case, right?
Yeah.
And then this is something you can do, right? So if they have like a classical strategy, this is what you do.
So then you know statistically the maximum amount
that
they can get of it
can
around.
Do,
yeah, you
right?
cannot go beyond that if you have like 1,000 times that.
And some assumptions go into this. So for example, the questions are really chosen at random, and we arrange these things locally beforehand, right? Okay. And then you make then you think, how would a quantum state behave? So like if instead of talking or arranging classical, we share some
questions
states,
are
right?
various measurements that the two experimentalists will do.
It could even be that like I take a photon and Sandu takes another photon, they are correlated, and whenever I get question 1, I make a certain measurement, and I say green for one outcome, red for the other. Right? If we do this, then we can win more than 3/4 of the time. Right?
Like
so this means that
87% of the time instead of 75.
So then this means that quantum theory does not satisfy this.
Yeah, it's above that 75 maximum.
It's above that, and requires we could win all the time if we could communicate.
Yeah, and now we know it cannot be a prearranged thing.
Be prearranged.
And we don't have general relativity giving us the option to communicate faster than light. So that's also ruled out.
Yeah.
So we have non-locality.
So this is a new phenomenon that shows that the particles in some sense communicate faster than light. And the fact that the results locally appear random, they cover this thing. And that's why it doesn't enter into contradiction with Einstein relativity. Only later. Yeah. So all an experimentalist can do can say, answer me question 1 or question 2, putting the measuring device in one way or in the other. Cannot force what is the answer the particle will do.
No.
So cannot force you to say red or green. Okay? You say whatever you want. Okay? So the experimentalist just sees whenever, no matter what I ask, you said sometimes red, sometimes green, 50%. So I don't know what has happened at the other end. Regardless on what happened at the other end, you just said 50% this, 50% that. So locally, I don't know anything. The other experimentalists cannot affect how many times you in my room say one thing or the other.
Yeah.
Only When later I go and meet with the other fellow experimentalist, we see that you somehow managed to take. So the existence of randomness is the thing that allows for this phenomena to happen.
And this then of course was deeply troubling for Einstein, but he didn't live the day to
he didn't live the day, and was deeply troubling to almost nobody else. Because people, again, they had other better things to do.
When those Bell inequality tests first came in, how was do you know what the physics community, what the response was when non-locality was sort of first established?
Yes.
When was this actually tested first?
Totally ignored, or almost totally ignored. Well, Clauser, that got the Nobel Prize, explained very nicely what he thought and how the whole thing came out. As a matter of fact, the way in which Bell did, there are very subtle things. Bell thought that you can never actually verify experimentally these things, in principle, because the particular inequality he found required measurements that are absolutely aligned on the two sides. And he knew that to have absolute alignment is impossible. You always have some tiny error. And the game that we presented here is not the game that Bell did. Is an improvement that allowed for not the necessity of perfect alignment, and it was due to Clauser, Holt, Shimony, and Horn, CSH inequality. So it required some update. And in fact, Abner-Shimony, the S in that inequality, told me how surprised Bell was that one can formulate a version of his inequality that could in fact be experimentally verified. So there were a few people that were interested in this, but the vast majority couldn't care less.
And that's strange, because going to sort of the implications of this. Okay, so now we have established that we have entanglement, or we have non-locality, because particles are entangled and they're sent apart, and we get these correlating above what is statistically possible
indeed.
under classical physics. So quantum theory is correct. Then when I read books, they say, and you corrected me earlier, that you said to me, you guys need to explain it to me, that free choice is also involved. But how I first read it was, now you have to pick. You cannot have localism, which we were used to from Newton and Einstein. I'm just affected by stuff which is here, I'm not affected by photons at the other side of the universe. That's just crazy. Yeah. So that's localism. And realism, the fact that things are real and they're independent of observation. And those two that are sort of two pillars in Newtonian physics, and we're all used to. Now you have to let go of one. That's what I read. And that puzzles me. So, but please explain.
There are different ways of putting it, but in a pragmatic way, what I would say, which is the most pragmatic way, forget the philosophy of it. It is very simple. If you and I would like to do that, we could not arrange by pre-arrangement at home. We will need to communicate. And since we need to give answers on the spot, we need to communicate faster than light. That is the main element in that. That pushes the boundary of the theory of relativity, which tells that this shouldn't be possible. But you say, look, this is what particles do, but I cannot hack their communication, because if I'm just here, I see random things. I don't know the other person cannot use this randomness to communicate things to me. Only when I would go and meet the other person, we see that the particles did something funny. But the fact that quantum mechanics is fundamentally probabilistic covers the fact that particles did something funny in the time in between. Okay? Mm-hmm. So there are many words that people put, realism and locality, and if you view it very pragmatically, that is a way of explaining what was, a way of looking at the results. And most people didn't have any use for particles at a distance. You have to realize that all the phenomena that people were interested, you know, why is this porcelain solid? Why is electricity going in the wire? Why is a helium atom, whatever? They all require particles in interaction. To try to think of what particles that don't interact, that are taking very far, what they do, nobody had any use for them. So that's why there was no established domain of science that would deal with that thing. So there were a few philosophers that were interested, and indeed a few experimentalists. But really, they were the exceptions, they were not the rule. So Clauser did his beautiful experiment. A bit later, Alain Aspect with Philippe Grangier, and those were the times before, you know, the quantum information started. When also on the theory side, most questions about non-locality were not asked. For example, nobody asked, okay, Bell gave a particular state that realizes this non-local phenomena. Are there other states like that? Okay. Much later, a state of three particles was discovered, GHZ, Grimberger, Horn, and Zeilinger, that also presents. But the main question, which other states? Are these exception, they are so fantastic states, or there are more? Was not asked until 92. That was in fact, you know, on a personal side, you know, I asked that question to one of my friends who was just telling me all the time about EPR. So tell me, Avi, which states do they violate? He said, I don't know, but you know all the literature. Okay, all the literature were a few papers overall by 92. And he said, I don't know. So it took me some years. It is an optimization question of many variables. Unless you do it in a clever way, it takes you a long time. And I abandoned a few times. So once, together with a friend of mine, Daniel Rohrlich, we proved that every single entangled state of two particles will lead to violation of, will lead to non-locality. And as before sending it to publication, I went back to look at the entire literature on the subject since Bell. You have to realize that if I could do that from 64 to 92, there were not too many papers. And it so happened that just the day before we wanted to send, a paper by Nicolas Gizen, who is also at this conference, appeared with the title, Every Single Entangled Pair Violates. So after almost 30 years, suddenly two papers appeared saying that.
Wow.
But this is a fundamental question.
Yeah.
Which states, if they are very isolated, it's probably something that, you know, it's irrelevant. What we found is that all of them, except for the extremely limited cases when the particles are not entangled, which is very rare, all the others lead to this.
And in theory, we're still talking particle level. Could this go for more bigger objects, for molecules? In
theory, yes, but we don't know at the moment. So what is the status of quantum theory versus big objects is...
But before we go there, because I had one question hanging.
Okay.
One question hanging, because I was asking you about the implications and localism, realism, and you were wanting to say there something as well, Lidia, because we had discussions about this, right? Sort of what to make from those.
You want to tell me to explain what the no-go theorem is?
What a no-go theorem is, and
the
exactly
uses are.
what I cannot believe anymore about nature after Bell inequality tests. What is sort of ruled out? So is locality definitely ruled out? I have to let go of that?
Okay. I have an analogy, Sandu.
You have an analogy. So tell the analogy.
Which I told Hans and Mike. So a no-go theorem is like saying, if I want to buy a meal, I cannot have it good, fast, and cheap.
Yeah.
I need to choose two. I cannot have all three, right? And a no-go theorem is the same thing. You say, there's like these three things that we'd like to have in nature. We can't have them all. The math is showing that we don't have them all. So one of them is being, compatible with the measurements we make of quantum mechanics. Non-signaling, meaning it cannot communicate faster than light. Realist in the sense of like these local hidden variables. And the fact that these measurements, these questions that are asked in the rooms are not pre-chosen in advance, right? That they're really random at a time.
Yeah.
Which is what some people call free randomness, some people call free choice, right?
Free choice, okay.
So now you have this theorem with these four things. And many physicists say, okay, we cannot have these four things.
You have to let go of one of them, or two?
If you let go of one of them, then you're fine
again.
Can come up with an explanation, yes. And then which one of them you let go of? For people who have to choose, like it's a matter of taste a lot.
Yeah.
A lot of times, like many people want to keep non-signaling because we like relativity theory, for example. So we let go of these hidden variables. Others don't. And then you try to look for more no-go theorems that are three assumptions.
It does hit on metaphysics, right? Because then it has to do with just your preferences on that level.
Well,
right? If Einstein, for instance, was a sort of, it was also open. The debates with Bohr, the moon is there. I like to think the moon is there, even if I'm not looking at it. That's just a preference about reality. I want stuff to be observer independent, to be real. And if you're more fine, no, I can live with sort of observer independent reality, then that's not such a big problem, right?
Well, I wouldn't actually say so. It's tempting. It's tempting to think that it's a question of preferences. But let's make it clear. There are facts of nature, that you predict.
Yeah.
If you say, I don't like that, I want to predict something else, it will turn out that you are wrong, because that is not what nature will show you. So it is very important that there are some objective things that are independent of who said that, what was the authority of that person, what are the preferences. The key of doing science is you make a statement about some results that an experiment that you haven't seen will give. Mm-hmm. And you try to make that statement as precise as you can. Okay, if it is very vague, then it cannot be tested. You say, okay, it will turn green. You do it, it turns red. Well, you have to do it many times to debug it, to make sure that you did it correctly. And if still turns out red and not green, you are wrong. No matter who you are wrong. And in fact, this is a great evolution in the cultural history of humankind.
Yeah.
That you don't need a debate. You don't need to listen for authority. It doesn't matter who is the person who said, what is the education background. It doesn't matter anything. There is any statement, the statement becomes scientific if you can make an experiment in order to see whether it's true or not.
I like that. There are people at this conference also using now words or terms like, isn't that Matt Leifer talking about sort of experimental metaphysics, that what we previously thought of as metaphysical debates of philosophers, that we can now just go and test stuff in a sense?
I think that you will interview Matt Leifer. He will tell it much better than I do.
Yeah.
But I would like to continue this.
Yeah,
thing.
sure.
So here the whole key is you have some sort of thought process that led you to make a statement. Anyone can make statements about what they believe this will turn out. Green, red, blue, pink, and so on. Now, some ways of thinking turn out to be more useful. They are correct intuition. If you would ask any random people to tell you, how to build this bridge in order for a car to be able to cross without the bridge falling, you would prefer to have a professional engineer than any random person on the street. So looking at the equations, it is not enough just to be able to solve a given situation, to compute what will happen in that given situation. It is important to have an intuitive way of thinking that can lead you to discover interesting situations, which then you will calculate. So it turns out that these preferences are, everybody is free to have their own preferences, but some of them are more useful than the other. Some ways of thinking of phenomena just led you into loops and loops, and you just, you get nowhere. There are different signatures of better or worse way of thinking. And the main signature doesn't always work, but the main signature is if you can find some really new question in your way of thinking. So what I mean really new, if you have a way of thinking that was generated by trying to solve a problem, you solve and then you ask another question, a follow-up of this. That is not really new, That is something obvious. You could always just ask a little bit more. If you find something sideways, you start by trying to solve a problem, and then this leads you in a completely different direction, and you discover something very interesting there, and leads you in a different direction, and you discover something interesting there. So much more than just answering your original question or a follow-up. Then that is a signature that your way of thinking is somehow useful.
Yeah.
In the end, you solve the same equations, but that is a signature that your way of thinking about it is correct.
And that has to do with intuitions, which is a nice word also. We started our conversation talking about the counterintuitiveness of quantum mechanics.
Indeed.
So I guess you, in your work, you have updated intuition, so to speak.
Absolutely.
You see the quantum weirdness with people, and then for you it stops being that weird because you update your intuitions and you're okay with randomness, you're okay with non-locality. So then I'm just curious how that plays out.
It's not only that you are okay with it, it's whether you can do something with it.
Yeah, check.
Whether you can go and thinking of that, you can find something sideways and discover something new there.
Yeah.
That is the basic test.
And how would you, if I'm sketching an extreme here, but in the interpretations in quantum mechanics, there are many flavors to pick.
Indeed.
And it seems to me that has to do, of course, with your intuitions, your preferences. So after we have Everett, who's a student of Wigner, student of Wheeler.
No, I don't know exactly.
But anyhow, we came up with the many worlds interpretation of quantum mechanics, which has to do with, okay, we have this weird, we also discussed double slit, so we have the waviness, we have that superposition.
Indeed.
What is it? This refers back also to Schrödinger. Is the cat really dead or alive? And you have many worlds, which, correct me if I'm wrong, I'm interpreting as saying, yes, both states are true, both at the same time. They're just a different branch of the wave function, and we have the multiverse and the many worlds. And that's an interpretation of the theory.
Indeed.
And then the question to me is do you think, for instance, is that a more fruitful or less fruitful one than saying, okay, let's go the other way? Not an ontic interpretation, but an epistemic one. Nope, we don't know what the superposition is because the theory is not about what nature is. It's a theory about what we can say about nature. This is referring back to what Bohr also, I think, said. So that's an epistemic. Are you following?
Yes, I'm following them.
Can you still follow me? And I'm curious, which one is, in your opinion, will lead to better questions or better experiments or will progress the foundations more?
Well, in my opinion, none of them are appropriate at the moment.
None of the interpretations of quantum mechanics?
None of them, yes. And it's not bad.
There must be a least worst. I mean, that's with democracies, the least worst system.
I believe that they don't capture the essential parts of quantum mechanics. But we are, in some sense, although we are 100 years after the basic laws were discovered, we are faced with a theory that is very, very different from all our intuition in everyday life. It's a complicated one. And many essential things for the theory have probably not yet discovered. You see, for example, non-locality is now considered to be one of the most important aspects of nature. And it took until 64 until John Bell. So from the 24 until 64, it took 40 years. And it's probably one of the most important aspects of nature. So we are probably still missing some. And trying to choose now among the existing catalog of interpretation, I don't think that any of them is right. The menu has to be increased. But there is something else. Instead of always struggling with the question, all of these come out because the theory predicts that things are in superposition, but we never feel confused. We never feel that we see two things at the same time. And that's what generated all this fantastic array of interpretations. Incidentally, some of them are not interpretations. Some of them are different theories which have different prediction than quantum mechanics, like the theory of spontaneous collapse of GRW. They could be tested. But others are pure interpretation. There are other ways of saying what we see.
Can I just interrupt?
Yeah, please.
When you say they can be tested, the reason why we've not completely ruled out some of them is that we need better technology to test it.
Yeah.
We need to make
positions
of larger and larger objects to kind of rule out this.
Yeah.
But some of them are simply not testable because they are constructed to predict exactly the same thing.
Mm-hmm. Yes.
Is sort of many worlds testable? Could we?
No, not at present. Many worlds will involve performing measurements also on human beings. And destroying them, erasing their memories and so on. But even then it wouldn't be clear because they may say, perhaps we should enlarge and measure everybody else who had a contact.
Before I go
that in some sense, that is non-testable. It is also a very complicated thing because when people say it contains nothing than the wave function, and then there is an entire collection of interpretations put on top of it. And basically, every single researcher that advocates many worlds has a different version of many worlds.
That week.
So there are many, many worlds. But I don't want to enter into them. The point is, there are many other things about quantum mechanics that are interesting. Like the existence of non-locality. That is a fact about nature that wasn't discovered. And without understanding that, it's clear now with hindsight that you cannot make progress. And there are many other things. So my personal view is that there are a few pillars on which quantum mechanics rests, and not all of them are yet explored to the full extent or even beginning to be explored. Apart from non-locality, that it's similar to Bell, this one of particles that got separated in space and are correlated in funny ways, there is another type of non-locality that involves the equations of motion of quantum mechanics. That was discovered, the first example is the Aharonov-Bohm effect. And the equations, the real equations of motion, the Heisenberg equation of motions that describe what happens with the observables, the quantities that we could measure, not with a wave function, they are non-local, the relevant ones. So that is very important to keep in mind. And it didn't yet have, let's say, applications. Like Bell inequality is now very famous because this phenomena of non-locality was put to use in quantum computing, quantum cryptography, a lot of things, so can lead to technological things. That moment of breakthrough didn't yet come for understanding the dynamical part of non-locality. The other thing is the fact that because the answer of a future experiment is not fully determined by the way in which you prepare, whenever you make a new experiment, you receive new information which was not there at the moment of preparation. In classical physics, if you know everything about the system at the initial time and you know all the forces, you don't need to make any other measurements. They will not add anything new. You can predict what they will tell you. Also, nobody needs to tell you about the past because you can retrodict it. But in quantum mechanics, anytime we will make a new measurement, because the result could not be predicted at the initial time, gives you new information. And that allows you to look at the time in between this, which is determined both by initial and final conditions.
This
so
is
the whole idea of what is time in quantum mechanics is far more subtle than what is time in classical mechanics. So I believe that this is another area that needs to be looked more careful.
Yeah, there's so much that it triggers, but this is Lidia, this is profound, right, in a sense, because you're hitting here also on, we haven't talked Schrödinger's cat yet so far. I think it's nice to go there if you're okay with that. When you say new information upon a new measurement, and I think the quantum father bore, what's that quote? There's no such thing as unperformed measurements don't have outcomes. And if you think, okay, that's a cryptic way of saying it, but it's just messing with our intuition that reality sits there, out there, and it has sort of the facts it has the physical properties it has, and when we come and look, it shows it to us, and it confirms our theories or not. And now we're saying, no, if you don't look, it doesn't. That information isn't there if I don't look. Does looking produce the information? Pascal Jordan said something like that. Observations produce.
That is again. So that is a quote from Asher Perez, who was, he had a deep knowledge of quantum mechanics. But the idea is that a measurement messes up with the measured system and may change its future. You cannot do it very gently. Like I may put my hand to try to find out where the cup is very, very gently and not disturb it. But in quantum mechanics, there is a limit, and I will always disturb things.
Always?
Yes.
Also measurement with a single photon measurement.
Otherwise, you don't get any information.
But
if you're not interacting with it.
Indeed. But more than that, it also refers of the past of the thing. That is, the thing that you measure was already predetermined. You know that the quantum mechanics, which is a mathematical tool that describes what your procedures, what your preparing procedures are, that is well defined. But what the result that measurement will do is probabilistic. Now, you may have different measurements that are in some sense incompatible with each other. Meaning, suppose even if I prepare a system in such a way that if I make measurement number 1, I know exactly what answer will do. Sometimes I can do that. But if I first measure experiment number 2, or let me call A and B. If I measure A, the result is clear from the prediction. If I measure B, B may give me some results, but I measure A afterwards, and it is no longer what it would have been if I would have not measured A. So measuring B disturbs whatever A will see. And in that sense, they are incompatible, and you could not say at the same time that this particular system has both a well-defined value for A and a well-defined value for B, because you cannot measure them at the same time. You have to give away your right of measuring one if you don't want to disturb the other. Then the question is, as Asher said, if you didn't perform the measurement, you didn't yet get a result. Okay? This was already known from the very early days of quantum mechanics. And many ways around them were tried, but okay, it's one of those funny phenomena. A more interesting question is, perhaps I nevertheless can measure B, but not exactly, but I could get a bonus. I can make a measurement that is slightly less disturbing. I pay the penalty that I don't measure B exactly, but A becomes more reproducible. So I can interfere with the B here in the middle, and I still have a measurement of A at the end and preparing the things before. And then the question is, what will be the results of this B? And sometimes they could be extremely surprising. That is, for example, the whole idea of pre- and post-selected systems and weak measurements discovered by Aharonov. So just to say that measurements that you didn't perform don't have answered, which was a very nice phrase discovered by Asher, is limited.
Lydia, do you want to add something, and maybe you can help explain
maybe
also?
Maybe
please.
just to bring it down. Okay.
Please do.
Okay. So in quantum mechanics, there's this thing that if I want to measure something and have a very definitive outcome, then to measure it like I'm shooting a laser at it, for example, or I'm letting a photon hit a detector, it's very disturbing for the state.
Yeah, check.
But one can make a gentler measurement, where then the idea is that I don't know, for example, like I want to see if the photons go through here, so I have something that interacts a little bit or weaves a little bit if it senses this photon here. It only disturbs its path a little bit, for example, okay? And then I need, of course, to repeat this many, many times in order to build enough statistics to see on average
because the
it went
thing that
through
you
there,
interacted
okay?
with, it's...
But in nature, it's not different from like doing a very strong, harsh, disturbing measurement once, right? It's just a different way to implement them. Yep. Mm-hmm. Is this...
Yeah, I'm following.
Okay. And now in standard quantum mechanics, we're used to thinking in like a very directional way. Like I prepare some state, do some transformation, measure, and that's the end of the story. But the theory is symmetric in time, so I can also think... Now I think of the two hands in being like in equal standing, right?
Yes.
Because what is preparing a state? I mean, if I want to prepare polarized photon, this in the end is also measurements. Like I send it through a filter, and only some come out that have that are turned in the right direction. So this is also measurement. Every preparation everything is measurements, right? So now I have this in equal standing with this, and they ask like, what would happen if in the middle I make one of these very weak measurements that only disturb a little bit, right? And there's things that we would expect if there were like hidden variables, if the answers to the questions were predetermined in some ways. And what the results of this experiment show is like, no, really not.
And the results are very surprising.
Very surprising.
And very unusual. So this entire area started after many, many years. So it was proposed maybe in the 80s, late 80s, and was mostly ignored. Again, one of those quirks of sociology, of science. But now they are becoming, coming into focus.
But I can only ask dummy questions on this topic. But is the sort of the arrow of time, which we know from classical physics, is quantum sort of does quantum not have the arrow of time?
Well, it does. It does. But where exactly the arrow of time comes is an interesting question. So as far as we know, the arrow of time comes from cosmology, from how the universe started,
entropy,
and so on. Yes, that it becomes more and more disordered with times. People thought that quantum mechanics, if the moment you perform a measurement, the wave function will do a collapse, let's say, the dramatic thing, and will give a result that is unknown from the beginning, will just continue to increase the disorder. So we'll introduce a time arrow of its own. Well, it turns out that it may do a disorder, but both towards the future and towards the past. So it is a departure from the way in which you see time in normal thing, but it doesn't signal out a preferred direction of time.
May I bring in just an alternative to Schrödinger's, or an addition to the famous Schrödinger cat thought experiment, which I read, and I don't know if I can reproduce it accurately, but I think you will both get the main idea. If we could somehow collapse the state, I think there was a thought experiment where they said, okay, if I shoot in a single photon in the box, that might trigger a collapse inside Schrödinger's cat box, and I wait for 8 hours. The gist of it was that you will find a cat that is dead already for 8 hours, or still alive for 8 hours and hungry. So it has to do with that if you wait and it's still in superposition, it somehow that past thing you did, that single photon measurement that did something. Does this make sense?
Well, the whole Schrödinger cat, the idea is that you may send a photon through a piece of glass, and it has a probability of going through or being reflected.
Yeah.
If you think in probability, but actually it goes in both ways at the same time, sort of, in a superposition, according to quantum mechanics. And if it goes towards the box where the cat is, may hit a detector and that release a poisonous gas, or let's be kinder, just something to make the cat sleep a bit longer. And but if the photon is the other way, and both of these things happen at the same time, that's the issue of superposition, then the cat is just running around.
Yeah.
Okay. The question is what happens when I open the box and I see the cat either sleeping or running around? Then it became clear that is the situation of the cat, and the cat was not in limbo in between these two things.
Check.
Which is different from what you may imagine if you would classically shoot a bullet towards this, which sometimes may penetrate this piece of glass, enter, and other times, but then it just went that way.
Yeah. Another
time, if you try with a cat, it may just bounce back from this thicker.
But do you what I was referring to, but I'm not reproducing it accurately. I should just read it out in the book or add this in a sort of in the notes. But I was referring to, I guess, what Wheeler said, sort of called, and this is of course not physics language, but like history creation of sort of the past is also created that somehow, and that was I referring. If you could somehow do that experiment that you only later check if the cat is either alive or dead, and then you collapse the state, then you also have the history of a for let's say already
where did the photon look? There are different ways of looking at it, and you may think of them, but the real test for the way of thinking that these two times are on the equal footing came, in my view, with the idea that you can perform some measurement in the middle that is not disturbing too much, and then you find characteristics that belong to both times. And you could immediately infer values for some quantities that if you were to compute everything step by step going forward in time would have required an enormous amount of work, and it will appear like the result of a whole conspiracy. While if you just look at influences coming forward and backward in time, the result immediately you can calculate and you can understand and you can do things with it. So the fact that all these phenomena in the middle became accessible, that gives a lot of justification of putting two boundary conditions. So again, where these two boundary conditions come from, they come from the fact that you start with something and may give a result. You start again with the same thing, may give another result. Now, the normal way people do quantum mechanics, they say, I start with something and I collect all the results. So I may do in between this and the final one, I may do all kinds of experiments and I collect all the results. But you can say, no, I want to look at the results of what I do in between these two times, only in the cases where the final result gives outcome one, not when it gives. So you get a more refined view about quantum mechanics. And you always want to look sort of the cleanest experiment. And these are the most refined way of preparing a system. And then suddenly an entire range of phenomena appeared, which you didn't see when you put everything together. They just washed out.
And what is sort of the experimental, empirical results around, because the retro-causality, this is just the word that pops up with me when you say all of this. Is there...
Maybe one way to look at it is like, these results don't show that information is traveling back in time. They just say it's much easier to predict what happened at an intermediate time if you think of it having come back in time.
Yeah.
Right? It's just a simpler theory. So this is kind of the way that...
And the math just gives you that.
Well,
that
the math
gives exactly the same thing as it will give if you go forward. However, the math that you do just thinking in the ordinary way going forward is extremely complicated. While the math putting like this is immediate and very intuitive. So the math itself tries to tell you there is something interesting there. Furthermore, the results here in the middle they have an interesting structure by themselves. So they open a completely new window of the quantum phenomena. But exactly as Lydia said, you could look at it like this. You don't. There are two issues here. Number one, that whenever you post-select, whenever you consider well-defined preparation and well-defined answer there, in the middle there appear interesting phenomena. Regardless on how you think of them. Those interesting phenomena that you discover there, they are there to stay. They are facts. It also changes the concept, because you find out that it's much easier to understand them with information like this than with information going upwards.
May I? Lidia, please.
Yeah, I have an analogy and a comment.
Yeah, please share.
So here's a simple analogy. So suppose you want to predict, You want to know if there was going to be a rainbow at 12 o'clock at midday, okay? And if you just look at all the initial states, so all the days where it was raining in the morning, right?
Yeah.
You need a lot of information about atmospheres, etc., to try to predict if there's a rainbow. But if now you look only at days where it rained in the morning and it was sunny in the afternoon, right? Now you have a much better indicator we'll get there, that there was a rainbow in the middle, right? It's not like information is traveling back in time. It's just like having information about the initial state and the post-selecting, like selecting only your samples where you get the rainbow in the middle, allows you to calculate the answer to your question, was there a rainbow, much faster. Except in the quantum case, instead of getting something intuitive like a rainbow, you get something very, very counterintuitive, right? And this is an example of what Sandu was talking about before, that, is this interpretation better than that or that? Like, does it give me an intuition that allows me to form better questions and find new phenomena? And this is precisely an example of this, right?
It is. Where this analogy
breaks down.
Well, it's a subtle thing. So you can look in more details at the weather today. You go on much larger scale, then you would know that later will be sunny. So you do have all the information here. And you could have done, and then you get your best prediction. When quantum mechanics, no matter what you do, you don't know the result of the final thing. So that really adds information which was not there. Yeah. Of course, it is very difficult by looking in the morning at the whole weather to predict that an hour later will be sunny. The system is very complicated. So for practical purposes, you may just look later. But the information, what will be, was already present. While in quantum mechanics, there is something new there. Yeah. And that's what, that twist is what brings to all these
super interesting
things.
I cannot help but make a sort of huge jump here, and please, and I don't expect you to say that is accurate, but I just want to sort of mirror it to you. At our channel, we are paying a lot of attention also to phenomena in parapsychology and tests that are just anomalous under sort of physicalism, right? Sort of, and that has to do with like the normal intuitions we have about the human mind, that everything is causal and it has to be local, etc. There is this test being done, and I can share the scientific work in the description below. I don't have the authors in my mind right now. Where in a test setup you have what they call retroactive priming in a psychological test. So, for instance, if priming has to do when you have to recognize a spoon in a click test. If I first show you a knife, you'll be faster to recognize the spoon than someone who was shown a tree or a car. I'm making a simple, but it has to do with the fact that the human mind you opened that drawer already for me, so I'm faster there, right? So that's just priming, and it's established psychologically in tests that if we prime people in tests, okay, check. They give us that result first. Now they did this crazy test that they thought, let's do retroactive priming. The test is done. So there was no. I afterwards show you now. You both have to click on a spoon, and now afterwards I show you a knife and I show you a car, and there is statistic significance that people who are retroactively primed clicked faster on the spoon, and this to me just relates to the things you are saying. But what's your response to this research?
So my response is, first of all, I don't know about it, and I cannot comment on what happened in that particular situation.
I understand.
However, there have been a lot of similar type of experiments, trying to guess cards and things like that. And it is very valid if you want and if you are interested to do those experiments, okay? Now, what happened in all of those is that as the experiments were improved, the phenomena became less and less visible. So the best interpretation is that they were just statistical not statistical fluctuation, no, I'm wrong. There were defects of the way in which the experiment was made. Somehow people were, prior to the thing, made aware. And it is very, very tricky to spot exactly what the problem with those experiments are. Incidentally, there is a very nice book that I would recommend to everyone. It's written by Feynman, so there are 3 talks given by him, and they are collected under the title The Meaning of It All. So in that he discusses experiments in parapsychology and all kinds of things in a very, very clear way. So I would recommend reading that. But to make things there is something that one needs to make clear. Whenever you have a question about nature that you phrase it in a well-defined way, you could start to make experiments, no matter how crazy it is. Do the planets tell me the way they are today that is a better day to go to the dentist? Well, you could make an experiment to look planets today and how many people went to the dentist and what were the results and so on. So it is, okay, it may be a waste of money. You may need to make your mind in advance. Would I spend my life doing those experiments or not? But this is a different thing. But once you have a question about nature that is well defined, where you explain what the result is that you want, not just something interesting will happen to me this day. That is not well defined. If I go to the dentist this day, I will need root canal. If I don't go, I will. Okay, the more defined it is, you could do experiments. The experiments may be difficult to do, but in principle they are doable. So it is a scientific question. The question is not scientific if you don't define its goals, if you just leave it vague. But again, not everything in nature, not everything in life needs to be scientific. You know, poetry and how you react to it, it's not a question of science. Love is not a question of science. You know, you don't need to be scientific for it to be a valid pursuit in life.
I'd like to ask to close our conversation with that sort of more meaning of it all personally to both of you. But just to throw in another one that just ponders me is that in the early days, I think, wasn't it von Neumann who had sort of the consciousness causes collapse interpretation, and that sort of died out. I think there aren't many people. There are some, though, that still pursue sort of that route, consciousness causes collapse. So the conscious observer does something in the measurement. Curious what both of your ideas are there. So classical Copenhagen interpretation of quantum mechanics basically said macroscopic objects we don't have to worry about. And draws this line between but correct me if I'm wrong, but between what counts as an observer and what is a system that can be observed, and where can we draw the line in between those? And I'm just curious because it seems that many people would agree any macroscopic object counts as an observer or can perform a measurement. Is there some different when we hit from molecules, we get to animals, people, and then we get to conscious animals, conscious beings? Does there happen something there when consciousness enters? Or is it just any macroscopic system counts as, can perform a measurement?
Well, okay. So at the moment, this question is outside the realm of experiments. Okay. Now, I would say there are 2 elements to this. Number one, is it possible? And whether it is probable. Okay. Well, there are different ways in which one could think of it. One of them is whether objects, macroscopic objects, big objects like this cup, influence the behavior of atoms or of different experiments at microscopic level just by being big. And then my brain is, well, it's similarly big to I don't know, your laptop there. It could be the case, it could be the case that there is a parameter of complexity, that the moment when you have structures that are complex, new physical phenomena will appear that are not yet captured in our theories today. And our brains are probably the most complicated, the most complex things. It's a possibility. Is it probable? Probably not. But there are different ways of thinking of it. Again, it is too vague at the moment to be able to do an experiment, let alone that technically is impossible. Okay. Of course, one can make silly jokes about it, whether a cat will make a collapse, whether a mouse will do, and a bacteria will do. But there are people that think that the level of complexity might lead to some behaviors that we cannot observe, that there might be existing in objects with less complexity, but we don't see them because the amount of times that those phenomena occur is less. Do I subscribe to this? Well, I don't want to waste my time thinking of, there are good questions and bad questions depending also the moment in history where you are. I don't think it is a productive question. The moment it will be possible to make experiments on brains, I presume some people will make them. Okay?
Yeah.
Yes.
And there are these, but then again, I think your response will be the same, that it's probably statistical fluctuations. There are these people who did
not
experiments.
Not only statistical, mistakes in the experiment.
Yeah, mistakes in,
systematic ones.
Yeah.
Systematic ones in the way in which the experiment was done.
And those experiments then, the people trying to, are just giving sort of the assignment to try to influence a random number generator, and they see sort of these very small fluctuations. That those are also those experiments, and then
it depends.
It all adds for people. When I read stuff, Jack, maybe there's something to it.
Consciousness
causes collapse.
It depends. The devil is always in details. Okay. So when you look at those experiments, you have to be careful. I really recommend this book of Feynman,
I'm gonna read it.
The Meaning of It All, where he explains it. So, for example, when people were asked to, the experimentalists would pick up a card out of a set of 5 different possible cards, and somebody will try to guess it, and they were guessing at an enormous rate. So it turned out that when they were just face to face, probably the experimentalists look at this in a different way, if it was a circle or if it was a star. And the medium was able to pick those things up. And then it was made clear that this is not a good way to run the experiment. Then a screen was put in between them. And the medium was still able to find, but not at this fantastic rate. The probability of finding was still better than random, but much, much less, which showed that the previous experiment was wrong. Okay? But now he probably picked on other things. So an example that Feynman gives, at a certain moment, the medium got tired. So then the experiment stopped because it was a big effort. How did they know that it was tired? Well, starting to give many wrong answers. So if you stop when wrong answers are given, obviously you skew the statistics. So there are very, very subtle ways in which an experiment can go wrong. So one needs to verify them. When there is a good theory backing it, it is much easier to spot whether experiments are wrong or not, because they fit or they don't fit with the theory. Even if they fit with theory, then it's even more dangerous, because it may be actually a mistake in the experiment, but you are not doing your tests enough. But statisticians became very good at spotting these things, and experimentalists are much more aware than they used to be. The way in which people do the experiments in high energy, in particle collisions, they go to long distance to avoid mistakes like this.
So there are interesting times ahead of us in that sense, that now we are able to perform measurements on bigger systems, right? I don't know what's now the limit to bring stuff into superposition. Where are we right now? Do you both of you know that experimentally?
No, I don't know. The last I knew were buckyballs, which are 60 carbon atoms in a very compact structure. Yeah. But I presume that people did since then. They did.
Is there one you would
complicated
one experiment, if you had to pick one, that you hope to see in your lifetime performed, if possible? An experiment you'd love to.
I will have to think of it.
Okay.
I don't know.
Oh, Lidia,
yeah,
you?
Yeah, I think you'll agree.
Which one?
Making like superpositions of big masses large enough that you can feel the gravitational. You can measure the gravitational field, and then you can see if like the gravitational field is in a superposition. That you can measure this if like the gravity is acting in it. I think this will be a productive experiment where I don't know what the, well...
You have a good guess.
I have a good guess, yes. I have a good guess, but I think it would lead to more research and to interesting questions. Yes.
I'm just hearing the words, of course, quantum and gravity, but then that seems to me like super relevant in all unifying theories, right? Because then if you can measure that and gravity, then we... For instance, Penrose's work sort of with objective collapse, which has to do with gravity, right? That stuff like that then can become clear to us, more clear.
Yes, clearer.
Yeah. And the meaning of it all, Sandu, has it affected working your whole career in quantum mechanics, those counterintuitive stuff you encountered and that you had to get used to? Has it influenced your personal life in some way, in your outlook on life, or just how you...
I'm just a happy person doing physics, whether it came from it or not, but I'm very happy. So
I think he's asking if there's any intuition you developed from studying quantum systems that now you apply.
And the way in which I settled the quarrels with my wife based on quantum physics? No.
Okay.
No,
Not a question
I'm very
for you.
happy to do it in the normal way.
Yeah.
Yes.
Check.
No. But just feeling good about life, it's a good thing.
Absolutely.
Yes.
And keeping an open mind.
Quantum mechanics didn't. And open mind is, again, open mind doesn't mean to be open to every silly thing. Yes, you need to keep an open but slightly educated mind and try not to fall for many, sideways and wrong ideas. Just to say I keep an open mind to everything, that is counterproductive.
Yeah, clear. And Lidia, has it for you, in a sense, has it influenced sort of just your outlook on things?
I guess, in a sense, like in the same way I said in the beginning, that quantum mechanics made me question my assumptions. I now take like this questioning the assumptions that go behind statements in general in life much more seriously, I think, than before. Yeah, and also maybe something that we didn't talk so much about today, but the way now in quantum mechanics, many things are relational to like what questions you ask, how correlated am I with the object I'm measuring, and so on. I think this also applies to other fields of life.
Yes. Thank you so much, Sandu, for your time. And I really enjoyed how you really explained stuff so carefully and in simple terms that I could follow. So thanks for that.
Well,
Yeah, and I
thank
think
you
our
for
audience will
inviting me.
really appreciate that.
Yes.
And
Thank you for the audience.
yeah, and if they can if they have questions, they can leave them in the comment section, and maybe we can follow up in a follow-up conversation with you if you like to do so.
Yes,
Lidia,
definitely.
thanks so much also for adding your thoughts and ideas and giving extra questions and explanations to the stuff Sandu said. And I think for both of you, it's also been nice to sit at this table because you collaborated in the past.
Absolutely.
Yeah, thank you so much.
Thank you.
Thank you, Hans.
Thank you for watching, and if you like the content we put out there, it would be very nice if you subscribe to our channel, share this content, and please leave your ideas and thoughts on everything we've discussed. And in this conversation, that's been a lot, but leave them in the comment section so we know what to follow up on, or maybe post next follow-up questions to Sandu or Lidia, and that just helps to know more about the world we live in. Thanks so much.
Thank you.
Thanks,
Goodbye.
Hans.
Thanks so much for watching. I hope you liked this video that dove into the puzzling phenomenon of quantum entanglement. In the upcoming months, we will publish more videos that cover the 2024 ICOCI conference on the foundations of physics. In those videos, we will cover other strange quantum phenomena that as of yet are not explained by the current interpretations of quantum mechanics. Stay tuned and see you in one of those videos.